So we want to sketch the graph, and mine is the region bounded by the graphs of y equal to 2e to the x, y equal to 2 minus x squared, y equal to, oh, I should, yeah, I'll say one more thing too here. Y equal to x minus 1, and x equal to 3. And we want to graph these things, and we want to see where they intersect. And now, well, let's just graph them. So 2e to the x has an intercept at 0, 2, and has the usual e to the x shape. 2 minus x squared is a downward opening parabola. It's been shifted up 2. So it's going to actually hit this point right here. And I believe it's going to be a little over here. So it's going to kind of look like this. And y equals 2 minus x squared would hit the x-axis at a positive square root of 2. Not that we need to write that down necessarily, but it's good to be aware of where it's intercepting there, just because I know that the square root of 2 is less than 3. So like there's 1, there's 2, there's 3. We're also going to graph x equals 3. I feel like I missed something here. No, I guess not. All right, I feel like the one I saw before had the y-axis as well, but whatever. Or the x-axis, I mean, sorry. Y equals 2x minus 1 is an upward sloping line that has a y-intercept of -1 and an x-intercept of +1/2. So it's going to go up this way. And it might not ever hit this it probably doesn't ever hit this exponential graph. In fact, I'm sure it doesn't ever hit this exponential graph, even though I've maybe drawn it so it looks like it could. And then finally, x equals 3 is way over here, which I'm going to kind of, even though I know it's way over here, I'm going to kind of draw it over here just to kind of get the point. Okay. So looking at this region here, I'm seeing that this is the region that is bounded by those 4 separate graphs. And it is the only region that has all 4 graphs as a boundary. So that's what we're kind of stuck with. So then if you ever have a region like this, you can't go right either way is kind of the worst way to say it. Meaning no matter whether you choose doing it in terms of x or doing it in terms of y, you're going to have to break this up into 2 pieces because it's got, right, if you think about using vertical cross sections going from left to right. So from left to right, the top function would always be 2e to the x, but the bottom function is going to switch from being the parabola to being the line. So we have to break it up right here. And that's actually what we're going to do. But I will point out, if you did it using horizontal cross section, it would actually be even worse. Because if you go from bottom to top, you've got some intersection point here, and then you go up, 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 and then your left and your right function is the parabola versus the line. And then as you go up a little higher, the left function is now the exponential, your right function is still the line. And then as you go even higher, your left function is the exponential, and your right function is this vertical line. So you definitely want to do the least amount of integrals you can. So that's, we're going to use vertical cross section. So I'm going to think about little rectangles in this section over here, and little rectangles in this section over here. So this first region, come on. That first region is going to be the integral of the top function minus the bottom function. And we can see from the graph that it goes as far left as 0. But what's this point of intersection here? Well, here's the thing. You could totally set 2 minus x squared equal to 2x minus 1 and solve for that. It's not too hard. But a lot of the times you're better off just guessing a likely candidate, and it's probably going to work out. A lot of the times they're going to be values that are nice. So before I even try setting 2 minus x squared equal to 2x minus 1, I'm just going to guess x equal to 1. If I plug in 1, 2, right, setting this function equal to that function, 2 minus 1 squared is 1. 2 times 1 minus 1 is also 1. So this is the point 1, 1. So a lot of the times you can just guess the point of intersection, and it's going to be faster than trying to actually solve the equation. Although you totally could solve 2 minus x squared equal to 2x minus 1. It's very solvable. You would get x equal to 1 and some other point down here where they intersect again, which we don't care about. So that's the upper limit is 1. Because these rectangles go as far left as 0 and as far right as 1. And then the other half, or the other integral, for this piece here, which I'll kind of draw in blue here. That one's going to be the integral from 1 to 3. It's got to be 3 because that's as far right as we can go. Of again, the top function, which is still 2e to the x, minus the bottom function, which is now y equals 2x minus 1. And that, in my opinion, is the hard part of the problem, is the setup. The rest of it is not too terrible. You will, if you actually, is it just a, actually look, no, you actually have to find the area. So I will point out, web work doesn't typically like or accept decimal approximations. So if you're going to find this, your answer is going to have some e's in it. So if I was going to integrate this, I would get the integral of 2e to the x is 2e to the x. The integral of minus 2 is minus 2x. The integral of plus x squared is plus x cubed over 3 from 0 to 1. And if we simplify that, or if we plug in, we get 2e minus 2 plus 1/3. And now here's an example of where we do have to actually think about plugging in the 0. We plug in the 0, we get minus 2 times e to the 0, which is 2 times 1 minus 0 plus 0. Yeah.
So, our teacher is just having us put it in
and do a decimal approximation, and the Desmos is accepted, or WebWorks accepted. Now that's bullshit.
She did like 5 decimals.
Well, that's garbage. You shouldn't do that. I mean, you can, but in my opinion, it is more correct to write 2e minus 2 plus 1/3 plus whatever this is going to be. So if we plug in, if we do this part over here, we get the integral of 2e to the x again, which is 2e to the x, minus the integral of 2x, which is minus x squared, plus the integral of 1, which is plus an x from 1 to 3. So this part's going to be, sorry, I got carried over here. So I get 2e minus 2 is minus 4 plus 1/3. And then here we've got plugging in 3, 2e to the 3rd minus 9 plus 3. And then minus plugging in 1, 2e to the 1 minus 1 plus 1. So I guess do whatever works best for you. I have strong opinions about decimal approximations, but that's fine. Yeah. The thing, I guess my issue with the decimal approximation is you could totally use a calculator to graph these things and find the area between them without actually ever doing any integration. And if your calculator is precise enough, you can get 5 decimal places without ever actually going through the process. Not that that's bad necessarily, just that it doesn't ensure that the students are actually going to learn what you're intended to learn. So that's what I'd say. You obviously all know you should do the integration to find the stuff, right? The process is what counts here, even though getting the right answer is what you're being graded on. Cool. So then you could do some stuff. You could also literally just type this into WebWork and it would work as well, or should work as well. I'm done with this problem. Unless there are questions. Are there questions about this problem? So again, what I would say is you definitely want to draw the region. You kind of, in my opinion, you kind of have to draw the region or graph it in some way. Like I certainly would draw it, like on a test, you don't really have another option, but definitely graphing is really the only way to see what you're actually trying to look at. Yeah. This one here?
Yeah.
Sure. So that is the integral corresponding to this region right here. Yeah. So we're going from x equals 0, right? This is the point 0, 2 to x equals 1, because it's the point 1, 1 of the top function, which is 2e to the x, minus the bottom function, which in that region there is 2 minus x squared. And then the other integral is this blue section here. Other questions about this? Probably ruined the saver under it. That sounds good. Okay. Fine. Next question. Sure, let's look at number 8. So same idea, right? It's another kind of thing where you have to graph the thing. So let's graph it and see what we've got. So this is where, if you had to do this on, so I mean, these problems are maybe not great test questions, but it's still worth thinking about what we would have to do if we didn't have any other tool to us. I'm not drawing perfect graphs, right? I'm drawing my best approximation of the graphs. So I know that 27 over x looks like 1 over x, but bigger, kind of. So 27 over x is going to be something like that. I might think about a couple points, like the point just for my own reference, 1,27 I know is on there. 27,1 is also on there. 3,9, 9,3. Right. There's some points on there that I could think about having in case I see something else that goes through one of those points. The next graph, oh great, y equals 0. Excellent. There's y equals 0. I do think it's worth labeling your graphs just so you know what things are. Let's see. The next one is, oh, this one isn't actually so bad. We've got, oh, I missed the y equals x squared. Sorry, y equals x squared. So y equals x squared is a good example of how thinking about the fact that this graph had the point like 3,9 is going to be really, really helpful. I know these graphs intersect, and I am pretty confident that I can guess the point of intersection. It's 3,9. You could also find it by setting these equal to each other, right? If you set 27 over x equal to x squared, multiply both sides by x, 27 equals x cubed, take the cube root of both sides, 3 equals x. So this point here is definitely the point 3,9. Look for the nice points. Not always, but a lot of the time with these regions, they've typically set I mean, I've definitely seen some garbage ones in the past where like you've got some terrible x-intercepts and things are really, really awful. But a lot of times people are going to try to write problems where the points of intersection are nice integer numbers. So if you can have a good guess, you might be able to find it without having to do the work of solving the equation. And then lastly, we've got the vertical lines, which are just really going to give us our x boundaries. We've got x equals 2 and x equals 7. So here's x equals 2 to the left of this point. And here's x equals 7 to the right of this point. And okay, let's see what this says. So we want the region bounded by the graphs of that. And again, I will point out the region has to be bounded by all, let's see, 1, 2, 3, 4, 5 graphs. All those graphs have to be boundaries of the region. So there's only one option. It's got to be this little thing down here. This is the only one that has all 5 of those graphs as boundaries. Cool. Just like the other, oh, no worries. It's totally fine to be like, oh, I should give you the attendance form though, just for you guys on Zoom. The attendance form. Oh, and if you guys missed the attendance form, you can always get it later at the end of class, or just go to Canvas. Sorry, words. At this point, so I want you all to take a minute to try and set up the 2 integrals we're going to need to set up to actually find this. So our area should equal an integral plus another integral. I'll even give you a couple of the limits of integration. There. You guys at home too, or wherever you're at on Zoom, try setting these up. My watch is almost dead. Okay. Oh. I was gonna give that to everybody. Oh. Welcome. Wait till I sneeze, then it'll. Well, it's a disappointing feeling. One of them anyway, having to sneeze and then going away. Really want to sneeze. All right, so for this first integral, starting at x equals 2 and going as far as x equals 3, right? Because that's where we have a break or a change. I said really more of a change, I should say. The top function is x squared. The bottom function is 0. You don't have to write -0, but it is good to think about because, well, in fact, I'll show you another example to why you should think about that. For the next piece, it's going to be the integral from 3 to 7 of, again, the top function, 27 over x minus the bottom function, which is again 0. This one's actually not too terrible to calculate. So calculating this one, it's the integral of x squared, which is x cubed over 3 from 2 to 3, plus the integral of 27 over x, which is 27 times 1 over x, whose integral is 27 times the natural log of the absolute value of x. I will point out, you can totally drop the absolute values here because the natural log of the absolute value of 7, well, the absolute value of 7 is just 7. The absolute value of 3 is just 3. So you can totally write this as 3 cubed over 3 minus 2 cubed over 3 plus 27 times natural log of 7 minus 27 times natural log of 3. And you can probably simplify that even further. 27 minus 8 is 19 over 3. And then this simplifies as 27 times the natural log of 7/3. So if you wanted to actually type in the exact answer into WebWork, that's what you would write. Or you could use a calculator to get your however many decimal places you need. No, I don't really care that much. I just care a little bit. Okay. So one thing I want to point out, just to kind of go along the way here, is if you had to find, say, if someone said to, I'm make it not too terrible, find the area between, what have I got here? Sure. Y equal to, sorry, brain, let me think for a second. X, sure. X times X minus 6, and the y-axis. So this one you could, sorry, x-axis, not the y-axis. Since we only have 2 functions to deal with, this is a situation where you can get away without graphing it. But I want to, well, we'll talk about this. So if I want to find how to integrate this, when you're doing an integral of just where 2 functions, like the area between them, in fact, we can totally graph that. No, I'm trying to wait. You can just find the points of intersection. So the x-axis is the line y equals 0. And you set these equal to each other. It's set up so you can find the points of intersection very, very easily. But now I want to point out, I'm going to do the wrong thing. The area, well, I'll just tell you, the area is not the integral from 0 to 6 of x times x minus 6. Because I didn't do the top minus the bottom. So if you graph it, here's y equals 0, aka the x-axis. And the parabola y equals x times x minus 6 has x-intercepts at 0 and at 6, but it opens upwards. So we're looking at something that looks like this. And the region is here. And if I actually want to find the area of that region, I have to do the top function minus the bottom function. So if you did this first way, you'd actually get a negative number. This would end up being the integral from 0 to 6 of x squared minus 6x, which is the x cubed over 3 minus 6x squared over 2. From 0 to 6, and if you plug in 6, you get 216 divided by 3, minus if you plug in 6, you get 3 times 36, and that is definitely a negative number. It's 72 minus 108, which is negative 36. That's not right. The area shouldn't be negative. So instead, what we have to do is this other thing, where you do 0 minus that. So this will end up equaling positive 36, which is the right answer. So just be careful, right? If you're trying to find the area between 2 curves, the answer should be positive. And to get it, we are always trying to do the integral of the top function minus the bottom function. Where the top is the top of my little rectangle that I draw, and the bottom is the bottom of the rectangle. Or if you're doing with respect to y, right minus left instead of top minus bottom. Do you know if we can expect the graphs to be given on? I don't know what to expect. Although I will say I do have some. I definitely, if you look on Canvas, I have some old. How do you say your teacher's last name? Okay, whatever your teacher's name is, starts with a Z. I have some of their old exams on Canvas. So if you look there, you might be able to get a better idea of what to expect for the next exam. I don't know off the top of my head. I can certainly look, but yeah, I don't know. My guess would be no. That I would typically, if I was writing these exams, I would not give you the graphs because my expectation would be that you should be able to graph it. That would be my expectation as a teacher. I'm not saying that's what your teacher is going to do, just that I could certainly, I would not be surprised if they did that. All right. We can look at one more question from the homework if anyone has one, but then I think we need to talk about volume. because that's where we're going next. Oh, yeah, sure. Up, sorry. And by up, you mean down, but yeah. By up, I mean down. Problem 11. Okay, someone said it, we're going to do it, and then we will move on to volumes. That said, I am in the drop-in room right after this today. So if you have questions about stuff and you want us to look at it after class, I'm happy to see you over there. All right, let's look at 11. Set of integrals to find the area of the region. Now, I will point out this says set up, so we're not going to actually calculate the area. To find the region between f of x equal to x minus 4 to the 15th power and g of x equal to x minus 4. This one is not as tricky as it might seem, but it's kind of, and they do give you the graph, right? The graph is awful. Sure, we can draw the graph. It's not much of a graph they give you, right? They're just gonna be like, there you go. Boop, boop, boop. I don't think they even give you any points of intersection. Like I can't tell because mine's a printout that's very small. On this problem, do they actually give you any points on the graph? Okay, cool. That's what I thought. So, but what we can definitely see, at least in this region here, certainly. Oh, but we're doing. I should also point out they're giving it to you as write it as the integral from a to 0 of something dy plus the integral from 0 to b of something dy. So here's what I know for sure. For a, sorry, that's not a. For a, which is my lowest y value, right? Because if I'm going from a to 0, it's from a negative number to y equals 0. That's not a. So from a to 0, the right function is the line and the left function is the not line. So if I'm going to do the integral from a to 0 of right minus left, that's going to be the integral from a to 0 of the line minus the other thing. We'll figure it out, don't worry. And then on the other hand, this other one's going to be switched. The integral from 0 to b of also right minus left. Again, right, we're going from y equals 0 to y equals b. We're going to have now the other thing minus the line. So we have a few jobs to complete. We have to figure out a and b are, which isn't as bad as it sounds. And then we have to rewrite these functions as functions of y. Yeah, functions of y. Okay, so let's find a and b. To find a and b, you're just finding where these functions intersect each other. So I'm going to set x minus 4 to the 15th power equal to x minus 4. Because even though I could solve for y, it's probably going to be easier to solve these equations as is. Now, I'm going to use the word wrong. The wrong thing to do here is to divide both sides by x minus 4. You can do that, and you'll get most of the solutions you need. Let me show you what happens if you do that. And you know what? I shouldn't say it's wrong because it's totally going to work out just fine. But the way I wouldn't always do this, if you divide both sides by x minus 4, you end up with x minus 4 to the 14th power. 14th power equal to 1. So what's definitely a solution? What's an easy number we could plug in for x so that x minus 4 raised to a power is equal to 1? Show me on your fingers. What can we plug in for x? Yeah. A whole hand's worth of fingers. 5. X equals 5 is definitely a solution because 5 minus 4 is 1 and 1 to the 14th power is 1. Show me on your fingers what the other solution to this equation is. Yeah, a couple less. 3. Because if x equals 3, 3 minus 4 is negative 1, and negative 1 to an even power is still positive 1. Now, we lost the solution. We lost x equal to 4. If you look back at the original equation, it's very, very clear that 4 minus 4 is 0, and 4 minus 4 is 0. So dividing by a factor like that means you occasionally lose sight of the fact that you have some solution by setting those two things equal to 0. If you're aware of that, you're fine. The way I would probably have done this if I was doing it in a more rigorous way would have been to have said x minus 4 to the 15th minus x minus 4 equals 0, and then factor out an x minus 4, and you're left with x minus 4 to the 14th minus 1 equal to 0, and then you're getting the same sort of stuff. You're getting x equal to 4 or x equal to 5 or 3. Yeah.
So we need to be solving for y.
Yes, we're going to get there in a second. So we just found all the x values. So here's x equal to 3, x equal to 4, x equal to 5. Finding the y values is super easy though, because if you plug in x equal to 5 to either equation, 5 minus 4 is 1, 5 minus 4 to the 15th is also 1. So when x is 5, the y value is going to be 1. When x is 4, the y value is going to be 0. And when x is 3, the y value is going to be -1. So I do think it's easier to solve for the x values than to solve for the y values. But either way, once you know the x or the y, you can find the other one just by plugging back into your function. So now we just have to write these functions as functions of y. So for the line, we would have had y equal to x minus 4. So if we isolate x, it's really straightforward. We're going to get x equal to 4 plus y. So that's what your line is going to be. So that's going to go in right there and right there. Your other, so we had y equal to x minus 4 to the 15th power. Again, solving for x, we'll have to take the 15th root of both sides. That's awful. Or the 1/15th power if you prefer. And then adding 4 to both sides, you get x equal to 4 plus the 15th root of y. And that's going to go in for your other thing. So at the end of the day, you would have something like the integral from -1 to 0 of 4 plus y minus 4 plus 15th root of y. And you probably cancel the 4's. Because 4 plus y minus 4 plus something, the 4's will cancel. And then for the other one, you just switch this fraction. Not too, well, no, it's pretty terrible. I'm not gonna lie. That's kind of the gross problem. Okay, so with the last 20 minutes we have, let's talk about some volume stuff. So volume is really a lot like area, at least the way I think about it, and the way I would encourage you to think about it, which is, I'll get these posted up as soon as I'm done with the office hours so that you can look at them later if you need to see them again. Well, actually, let's just do an example. We'll talk about it. So let's do the following. Let's find the volume. Oh, and I'll take a look in a second. Of the solid formed when the region A in quadrant 1 bounded by, there's so many words to write for these questions, y equals x cubed, y equals 0, and x equals 2 is revolved about the x-axis. So what I would say for these is you're always probably going to want to draw a picture. So I'm going to draw the region, and I'm going to think about the region in the same, just like I would if I was trying to find the area of the region. So I've got y equals x cubed, y equals 0, x equals 2. So I'm going to draw those graphs. Y equals x cubed. I'm not going to draw them perfectly. Here's my y equals x cubed. Looks something like that. Y equals 0 is your good old x-axis. And x equals 2 is this vertical line. And this point of intersection, well, if x equals 2 and y equals x cubed, then this is the point 2, 8. Not that you necessarily need to know that, but it's good to be aware of it. So I'm revolving this around the x-axis. So here's the idea. We're going to take one of our little strips, one of our rectangles. We're going to ask ourselves, okay, if I draw a rectangle here, well, I'm not trying to find area anymore. So I'm not going to do the integral of just top minus bottom. I'm trying to find the volume of the shape I get if I revolve this thing around the x-axis. So I'm going to think about what happens if I revolve just this little strip around the x-axis. And here's what's going to happen. This strip I like to draw it over here just so it's kind of out of the way. If I revolve that around the x-axis, it's going to look like, well, kind of a circle, yeah, but it's going to be a circle with some thickness, or as we like to call it, a disk. So we get a disk, and the volume of this disk is the area of the circle, pi r squared, whatever the radius is, times the thickness, which is a small change in x. Right. So that's the volume of that disk. But again, that's just one disk. We want to add up the volumes of all the disks. So the way we quote unquote add up all the volumes is the total volume is going to be the integral from as far left as x equals 0 to as far right as x equals 2 of pi times our radius squared dx. We're just adding up all the volumes of all the disks. Now, the radius of this disk is variable, right? If I drew my disk, instead of drawing this one here, if I drew it right here, I would get a much smaller disk. If I drew it over here, I would get a much larger disk. But the idea is the radius is just how far away the function is from the axis of rotation or from the center. And that's just what, in this case, what the function is. So in this particular problem, our radius is just the function x cubed. That's it. So now, if I want to calculate this volume, it's going to be the integral from 0 to 2 of pi times x cubed squared dx, which is not too terrible to calculate. That's going to be the integral from 0 to 2. We usually bring the pi out in front, and x cubed squared is x to the 6th. We integrate that, we get pi times x to the 7th over 7 from 0 to 2, which ends up being pi times 2 to the 7th over 7 minus 0, which is 128 pi over 7. Cool. And not that you need to draw what the rotated figure looks like, but people often like to just kind of get an idea. So if you actually were to draw this thing, which I'm not always excellent at doing, but the easiest way to try and draw these, if you need to draw them, is to draw the kind of outer boundary of your region and then reflect it across the axis of rotation. So I'm just going to flip this over and draw it down here and then try and make it look 3D. So it kind of looks like that, where I've got these little, like, here's my little disk right there. Or, a little one right there. That's the idea, is we're just adding up all these disk volumes to get the total volume. Kind of neat, I think. And I will say, this idea always works in that you're always just rotating this region around. And so it's really going to make sense to think about, that's why we talked about the strips before. So if you think about having a strip there, you're just saying, oh, well, now instead of finding the area of this rectangle, I'm finding the volume of the disk generated by revolving the rectangle around the axis of rotation. And this method is called the disk method. So if you're trying to find, in general, I'll say, let me write it on the next page. So we have the disk method, which is very generally, volume is the integral from some a to b of pi times your radius squared dx. And typically, we bring the pi out. So we will, and I'll be perfectly frank, I often forget about the pi. I will bring it out and then I'll totally forget to write it on the next step. So be careful. Remind me if I miss it, because I will probably miss it. But just to the point, we could also write this as pi times the integral. Whoops, you got a little blur there. I was pounding things like that. Sorry about that. There. Did I fix it? It did. That's great. Okay. And what I want to mention here is that this capital R, this radius here, that is going to be a function of your variable. This is going to be a function of, in this case, x. And you can totally also do this in terms of y in the same sort of way we did area in terms of y. So let's look at another example. Actually, let's look at the same example, but now instead of revolving around the x-axis, we're going to take the same region revolved around the y-axis. Typically in the 16 series, we do not cover the shell method. If your teacher does, let me know. I doubt they will because they've taught, I've followed them before and they haven't taught it. So I don't think it'll come up. But if your teacher says something about shell method, do let me know and we will cover it. But we only really have to deal with the disk method, or what I should really say is the disk/washer method. They have two different names. They're really the same thing. One is just the more general version of the easier thing. Kind of like how taking the derivative of log base b of x is 1 over x natural log of b. And that's really just the rule that works for any logarithm, even the natural log of x. We just have a slightly easier version of the rule for that. Kind of the same idea. So to do this one, we're going to draw, I still think we should draw the picture. Here's my region. Whoops, except I drew it wrong. It doesn't really matter, but it kind of matters. Shouldn't draw your region wrong. Okay, boo, boo. Okay, fine, new page. Whole page just for the disk method. Fine. Just a, natural renewable resource. Okay. So same region, y-axis. Let's draw it correctly this time. It looks like y equals x cubed, which looks more like this. And I'm going now around the y-axis. So let's draw my region here. We have to use strips or cross sections, and this is a true thing about the disk/washer method always. When you're doing the disk or washer method, which is our only method, your strip has to be perpendicular to the axis of rotation. So in the previous example, our axis of rotation was the horizontal x-axis. Cool. And our strips were vertical. They're perpendicular to each other. In this situation, our axis of rotation is the y-axis. So our cross sections or our strips have to be horizontal rectangles, meaning we're doing things in terms of y. Okay. Also meaning we're going to have to use the washer method because, well, and I'll tell you, the disk method is what we always end up using if your region is flush with the axis of rotation, or in other words, if the axis of rotation is one of the boundaries of your region. So in the previous example, right, keep going back to this. In the previous example, the axis of rotation was the x-axis, and the x-axis was one of the boundaries of our region, which is nice. Basically, when you rotate this thing around, you're not going to be having some like gaping hole in the middle. On the other hand, when you rotate this thing around the y-axis, you are going to have this gaping hole in the middle of stuff missing. We're going to have to subtract that out. You could also say this region is certainly not flush or next to or abutting the axis of rotation, whatever word you want to use. Or you could say the axis of rotation, which is the line x equals 0, is not one of the boundaries. Okay, so in this case, we are going to use the washer method. It's really not that much force. It's got like one extra tiny piece, totally fine. Okay, so if I rotate this little region around this little rectangle around the y-axis, well, I'm going to get something that kind of looks like a washer. That's why it's called the washer method. Right, if I rotate this around, I get something that looks kind of like this. There's our washer. Right, if you take this little rectangle and you rotate it all the way around, but it's not like it's missing all the stuff in the middle, you're going to get a shape like that. And this washer has a little thickness, dy. It's got an outer radius, big R, and it's got an inner radius, little r, which we can actually find, but I'm going to be general at first. So the volume of this washer instead of just pi r squared d whatever, dx or dy, it's going to be the big circle area minus the little circle area, and then times the thickness. Because we don't want all of the circle, we want the big circle and subtract out the little circle. So this is going to be, the volume of this washer is pi times big R squared minus pi times the little radius squared, all times the thickness. And we should probably factor out the pi because it makes sense. And when you do this, you make sure that you do the big function squared minus the little function squared, not the big function minus the little function quantity squared. It's a different calculation. In this particular example, well, I guess we have to find the functions first. This function was x equal to 2. This function was y equal to 0. And this was y equal to x cubed. And if we solve for x, that's going to be x equal to y to the 1/3. So actually using the functions we were given, the outer function, the one that's further from the axis of rotation, is x equal to 2. And the one that's closer to the axis of rotation is x equal to y to the 1/3 squared. So that is the volume of this washer. So then if we want to find the total volume, well, then we have to integrate, right? We are adding up, right? I really, and I say it like every time, but you really do want to think of integrating when you're talking about volume or area, as you're just adding up a bunch of smaller areas or a bunch of smaller volumes. I'm adding up, like your book has some good pictures of like a bunch of like discs kind of stacked on top of each other. And the idea is you're adding up the volumes of all these discs. So here, how low would my washers go? And how high? Let's see. So right down here, like here's the y equals 0, 1. And then you go as high as, oh, what was that point again? Yeah, that point's 2,8. So here our limits of integration are from 0 to 8. If it's a dy, your limits of integration should be y coordinates or y values. So we're going from y equals 0 to y equals 8. And then it's just going to be pi times the outer function squared, which I wrote as 4, even though I should have written as 2 squared, minus y to the 1/3 squared is 2/3. And then the integrate. So usually these problems, the setup is often more of the challenge. Integrating it's still not always super easy, but setting it up is the hard part. Calculating this, the integral of 4 is 4y. The integral of y to the 2/3 is y to the 2/3 plus 1 divided by 2/3 plus 1 is like multiplying by the reciprocal from 0 to 8. Okay, let's plug those in. We get pi times 4 times 8 is 32 minus 3/5 times 8 to the 5/3 is, guess what? 32. Minus 0 minus 0. Now here's a cool trick I've seen over the years because I've seen these a lot. I have pi times 32 minus 3/5 times 32. Now I would really prefer not to do 32 times 3/5, which is 96/5, and then get a common denominator and do 160/5 minus 96/5. That sounds terrible. Here's what you should do instead. Factor out of 32. 32 pi, you're left with 1 minus 3/5. It's way easier. 1 minus 3/5 is 2/5, and 32 pi times 2/5 is 64 pi over 5. Much nicer. Or use a calculator. What I would say about this here is what we've really calculated is we've calculated let me draw a picture here. We have done 2 integrals. The integral from 0 to 8 of pi times 2 squared, which is really just, if you look at my picture, that's just this cylinder with a radius of 2. Which makes sense because the volume of a cylinder is just pi times the radius squared, right? It's area times height. Pi r squared times h, which is exactly this. This is pi r squared, and then when you integrate it, you're going to multiply by end up multiplying by 8. So we did, and that's going to be 32 pi. Pi times 2 squared times 8. And then we subtracted off the volume of the inner part. So we did this, and then we did minus the volume of the inside part, which is going to look like, it's going to kind of draw it here. Plus, right? We subtracted off the volume of this, which we used the disk method to find. So the volume of this was exactly the integral from still 0 to 8 of pi times my radius squared, which was the cube root of y squared, y, which is exactly pi times the integral from 0 to 8 of y to the 2/3. So that's why the washer method really works the way it works. You're just doing the outer volume minus the inner volume to get what's left over. This is kind of a weird shape. I'm not particularly good at drawing it, but you could imagine taking a block cylinder and then kind of hollowing out this shape from it to get something. Be kind of like, it'd be a neat bowl, right? If you had like this giant cylinder and then you like made a bowl out of it instead of just making it like a cylinder container. I think it'd be kind of neat. Out of like a block of wood or something. I don't know. Chisel it out. Anyway, that's the idea with the washer method, is that you're always doing the big radius squared minus the little radius squared. Now I'll point out, if you went back to this original example, you could use the washer method, where your large radius, oh, sorry, that's not the example. Apologies. Paper. You could use the washer method and say that the big radius is x cubed and the little radius is 0. But you wouldn't do that. You would just say you're using the disk method. So really, the disk method is the washer method. The washer method is just the generalized version where you have an outer radius and an inner radius. Or the disk method, you have an outer radius and your inner radius is 0.